Hello everyone and welcome back. Today we are diving into part 4 of our series on thermal radiation. We're going to explore a remarkably elegant framework, modeling thermal radiation as an electrical network. Let's see how this unfolds. Before we get into the mechanics, let's lay out our core learning objectives. We will master radiosity, quantify surface and geometric resistance, and learn to synthesize complex radiation problems into solvable electrical circuit analogies, which will then apply to real-world engineering scenarios. To understand why we need this network approach, let's examine the problem of infinite reflections. As we see mapped out on the left half of our slide, dealing with an ideal blackbody is simple because the total energy leaving the surface is purely due to emission. The equation positioned at the bottom left defines the blackbody emissive power, which tells us that the ideal emission depends solely on temperature and a fundamental constant. However, if we shift our perspective to the right half of the slide, the reality of real-world surfaces introduces a major complication. Real surfaces are opaque, diffuse, and gray. When a ray hits a surface, it reflects, strikes another surface, reflects again, and bounces indefinitely. Tracking these infinite individual rays becomes mathematically intractable without a single, unifying metric. That brings us to our unifying metric, radiosity. By definition, radiosity is the total radiation energy leaving a surface per unit time and per unit area. If we look right at the center of the slide, the diagram illustrates how radiosity compresses infinite reflections into a single manageable quantity. We see incoming incident radiation striking a real surface. Part of that energy is reflected away, and simultaneously, the surface itself generates its own emitted radiation. Radiosity is simply the sum of these two streams, the reflected component plus the emitted component. By tracking this combined energy stream instead of separate reflections, we can collapse a highly complex tracking problem into a single known variable at the surface. Now let's translate this into a circuit analogy by defining surface resistance. The conceptual idea here is that a real surface's deviation from a perfect blackbody acts as a physical restriction to heat flow. Following the network diagram on the right side of the slide, we can establish our circuit equivalence. The ideal blackbody emissive power acts as our voltage source. The actual radiosity represents our node voltage, and the net heat flux leaving the surface acts as the electrical current. The expression enclosed in the box on the right quantifies this surface resistance, showing that it depends on the surface area and its emissivity. Notice the expression at the bottom right. It represents Ohm's law for a surface, where the heat current equals the potential difference divided by this surface resistance. For a perfect blackbody, the resistance drops to zero. Once radiation leaves a surface, it must travel through the physical geometry between that surface and its surroundings. This brings us to space resistance. As outlined on the left, the physical geometry itself limits the flow of heat, and the key variable dictating this bottleneck is the view factor. A smaller view factor means the surfaces see less of each other, creating a tighter bottleneck and increasing the space resistance. Looking at the circuit layout on the right side of the slide, the space resistance connects two different radiosity nodes. The equation highlighted in the central box defines this geometric space resistance, showing that it is inversely proportional to the surface area and the view factor between those two nodes. The less they see each other, the higher the resistance. Now let's synthesize these pieces into a complete two-surface network, which we call a resistance bridge. In the enclosure sketch at the top center, we see a net heat transfer flowing from surface 1 to surface 1's surroundings, terminating at surface 2. By mapping this out into a thermal circuit below, we reduce a complex enclosure calculus problem to basic Ohm's law. We have a series circuit starting at the ideal blackbody potential of surface 1, passing through its internal surface resistance to reach the first radiosity node. From there, the heat current flows through the geometric space resistance to the second radiosity node, and finally passes through the second surface resistance to reach the ideal blackbody potential of surface 2. The governing rule here is that the net radiation flow through a surface resistance must perfectly equal the flow through the space resistance. Let's look at how this simplifies for standard industrial geometries. In the table filling our slide, we examine three classic configurations, where the view factor from the inner surface to the outer surface is exactly equal to 1, meaning the space resistance simplifies dramatically. In the first row, we have infinitely large parallel plates, where the surface areas are equal. The expression on the far right defines the net heat transfer equation for parallel plates, showing how it depends on the temperature difference and both emissivities. The second row covers infinitely long concentric cylinders, and the third row outlines concentric spheres. For both cylinders and spheres, the net heat transfer equations on the right incorporate an area ratio based on their radiuses. In all three cases, knowing that the view factor is unity allows us to bypass complex integration and directly calculate heat transfer using surface properties. Now that we know how to model radiation networks, let's look at a powerful engineering application: obstructing heat flow using a radiation shield. Our goal here is to drastically reduce radiation heat transfer between two surfaces. Following the notes on the left side, the method is simple. We insert a thin plate or shell with highly reflective properties, meaning it has a very low emissivity between the hot and cold boundaries. If you observe the physical diagram on the right, you can see how the thick arrows representing the large radiation flux from the hot surface are heavily attenuated as they pass through the shield, resulting in a much smaller heat flux reaching the cold surface. This is vital in cryogenics and space applications. Let's look at the mechanism behind this reduction using our network expansion analogy. As we see mapped out on the left side of our slide, a standard two-surface system without a shield has only 3 resistances in series, as shown by the network diagram and the corresponding net heat transfer equation at the bottom left. Conversely, if we shift our perspective to the right side of the slide, placing a single shield introduces 2 brand new surface resistances and splits the space resistance into 2 segments. Look at the expanded pink circuit at the top right. We've packed multiple new resistors into the line. Consequently, the equation spanning across the bottom right shows a much larger denominator. By adding these extra resistance terms, we choke the thermal current and drastically drive down the net heat transfer. We can scale this concept up to any arbitrary number of shields. The primary expression highlighted at the top of the slide defines the total heat transfer when an array of multiple shields is inserted, adding a series of resistance terms for every single shield layer. If all surface emissivities in the system happen to be equal, this complex relation collapses into the beautifully elegant formula shown right in the middle of the slide. This expression dictates that the net heat transfer with multiple shields is simply equal to 1 over the number of shields plus 1, multiplied by the unshielded heat transfer. The bar chart filling the bottom half illustrates this steep exponential decay. Adding just 1 shield cuts heat transfer in half, and by the time you reach 20 shields, heat transfer drops near 0, a technique routinely used in cryogenic insulation. Let's pivot to another critical engineering scenario: understanding sensor errors due to radiation. This is what we call the thermometer short circuit. As outlined on the left, there is a common illusion that a thermometer placed in a gas duct rarely measures the true fluid temperature. In reality, the sensor acts as an energy junction. If we examine the physical diagram on the right, the thermometer bulb gains heat via convection from the passing hot gas stream, but it simultaneously loses heat via radiation to the much colder duct walls. Because of this dual pathway, the measured temperature recorded by the thermometer settles at a steady thermal equilibrium that sits precisely between the true fluid temperature and the wall temperature, leading to a significant measurement error. Let's quantify this error and look at the engineering solution. Following the math laid out in the top half of the slide, we perform an energy balance where the convective heat rate into the sensor must equal the radiative heat rate leaving it. The equation enclosed in the pink box in the center defines the true fluid temperature as a function of the measured temperature plus a correction factor. This diagnosis tells us that the measurement error is most severe when the convection coefficient is low and the sensor emissivity is high. To fix this, look at the engineering solution illustrated at the bottom right. By applying network theory, we coat the sensor with a low emissivity material and surround it with a physical radiation shield. This effectively breaks the radiative circuit, blocking the sensor from seeing the cold walls and forcing it to converge accurately on the true fluid temperature. To wrap up our discussion, let's review the key takeaways. First, remember that thermometers and gas streams do not measure fluid temperature directly. They settle at a thermal equilibrium between convection and radiation. Second, inserting radiation shields introduces new surface resistances that effectively choke the heat flow, where an array of shields scales down the heat transfer predictably. Finally, to minimize radiation errors, we must either use low emissivity coatings or increase local flow velocity to boost convection. Thank you for joining me for this overview of modeling thermal radiation as an electrical network. I hope this helps you approach these complex heat transfer problems with more clarity. See you in the next session.